All right? So the natural thing here to do would be x over 2 squared plus y over 3 squared. That's a, intermediate thought. But that gives me cosine squared theta, cos squared beta, right? Plus sine squared theta, cos squared beta. But you see I've got a common cos squared. So I got myself cosine squared theta plus sine squared theta times cos squared beta. That, of course, is just cos squared beta, right? But then, okay, so you see I just used that this is 1, of course. We know that. But we also know that cos squared beta minus sin squared beta is what? Equals 1. And that tells me for my equations here that x over 2 squared plus y over 3 quantity squared, what? Minus sinh, which is z squared, equals to 1. And there you go. Was that hyperbola to 1 sheet, 2 sheets? I forget, but one of them, they're hyperboloids. That's my thought process. I mean, so, other questions?
Number 17, I think. The very last one. Yeah.
Let's see here. We got, what we got? B and C are perpendicular constant vectors. So what's that tell you? That tells you that B dot C is 0, right? It also tells you that B prime and C prime are 0. They're constant vectors, right? That much we were given to start with. And I tell you that the velocity is B plus T cubed C. And the velocity of a ninja, of course, at 111, I should change these all over to Trump problems. Velocity of a Trump. That would make them more relevant, since everything's about Trump now. But anyway, at 111 at time 0, and then find the position and acceleration of the ninja at time t. Zero. Oh, so here I'm telling you that the initial position, I'm telling you that r of 0 is 111 here, right? Acceleration is not given, but you can derive it by differentiating that. And I say find the tangential component of the acceleration as best you can with the given information. Yeah. What's the point of this problem? The point in part is to test if you've actually been paying attention to the symbolic properties of differentiation. We talked about differentiating dot products, right? I talked about how constant vectors behave under differentiation, things like that. Not too much. So this is, this is a bit of a moderate challenge problem, I would say, maybe a straight up challenge problem. I didn't expect everybody to get this problem right. I mean, I was happy when people did, when I gave it. Okay, anyway, to the point. V squared is V dot V, right? So that, why is it just B squared plus T to the 6 C squared? Where B squared and C squared are the magnitude of B squared and the magnitude of C squared, according to our usual notation. Where did the B dot C and C dot B terms go in the dot product? Right. And why was I taking the dot product of V and V? Because remember, the speed squared is the velocity dot the velocity. Fundamental fact that you should remember: to calculate the magnitude of a vector squared, we take the dot product of the vector with itself, right? Anyway, so that's B squared plus T to the 6th, and then so, well, apparently V is the square root of B squared plus T to the 6th C squared, so dV dt, right, is 6T to the 5th C squared over the square root of 2 B squared plus T to the 6th C squared. Why didn't I have like a dC dt term and a dB dt term here? I mean, I'm assuming something that you could easily prove. If the vector is constant, what can you say about its magnitude? If If you have a constant vector, does it have constant magnitude? Right. You could prove this. If you have a vector with constant magnitude, is it a constant vector? I mean, if it's raining, the ground is wet. Surely if the ground is wet, it must be raining. Right? No, wrong. I mean, we have constant speed vectors that have constantly changing direction, right? But if the vector is constant, it certainly has constant magnitude. I mean, you got to be careful about the order of implications, but certainly a constant vector has constant magnitude. So B and C, without the vectors, those are the magnitudes of B and C respectively. Those are constants. And that's why I differentiate them like they're constants down here. But remember, we worked out the other day that dv dt is what? That is the tangential acceleration. Remember? We worked this out. So there's the tangential acceleration. On the other hand, you can straight up calculate the acceleration by just differentiating the velocity, like so. dB dt as 0. ddt of t cubed c would be 3t squared c equal to a. Now, we know that that has two pieces, right? That's got the tangential and the normal. Although, I think I had the good sense to not ask about normal here. Good, yes. So there's my acceleration, there's my tangential. What else was I asked? Oh, position, right? To find the position, we integrate the velocity. So how do you integrate a constant vector? You just do t times the vector. Again, a little theorem you could prove. To integrate, I tried to point this out when we did the constant acceleration due to gravity example. We noticed that we could either do component by component, or we could just treat minus gz hat and just integrate at the level of vectors. I tried to make this point to you there in this semester. I may have failed. But it's kind of neat, right? To integrate b, let me just say it again here. If b is a constant vector, this actually makes sense. If we're integrating b dt, this is essentially a theorem that this is b times the integral of dt. I mean, there could be a function here. If this is constant. Constant vectors pull out of integrations, just like constants pull out of integrations. So when I integrate the constant vector b over time, I just get tb. When I integrate the t cubed times the constant vector c, I just integrate the t cubed and the c rides along. I get 1/4 t to the 4th c. And then plus c1, which is the integration to constant vector. But I know that the initial condition is that r of 0 is 1, 1, 1, which has to match this, right? Which then shows me that the c1 is actually 1, 1, 1, and there's the position. So I like this problem. There's a lot to it. It's definitely not an easy problem. But other questions? Somebody asked me an email, like, you didn't understand like the TNB curvature torsion thing. You didn't understand like those problems. And that comment to me, it made sense, right? Because that communicates a misunderstanding of the purpose of what we're doing. When I tell you guys about the T, the N, the B, the curvature, the torsion, I'm not really trying to help you solve a particular type of problem. It's not what that's about. So often in mathematics, we say, here's a problem. We're going to learn how to solve it. That's not the format that we're engaging in with the TNB discussion. It's discussion discovery. I'm showing you concepts that hopefully elucidate the structure of curves. The point of the discussion is for you to learn the definitions and be able to do calculations similar to the ones I've done. There's not standard canned problems to do per se. I mean, I can point out a few of them, but that's not really what we're after. I mean, the standard problem that you'll see I ask on the test is pretty much this, you know, find the TNB and curvature and torsion for a curve. I mean, I guess there's a problem that you can learn to solve, but that's not really the motivation. The motivation is to try to gain a deeper insight into the geometry of curves. Anyway, any questions about this? Yeah.
Are you going to have this math battle on
Oh, I was planning to go post this right after class, yeah.
Okay.
And also the solution to mission 2. Any questions there?
I have a question on grading.
On grading?
Are the points for this first math battle split between the math we took on Wednesday and the quiz we'll have on Friday? Because quizzes aren't listed in the course planner, just math.
Oh, really? Did I not? Am I not giving quizzes? Oh. Well, that's nice.
So no quiz. Yeah, no quiz tomorrow.
Well, no. I mean, if I didn't say there's a quiz in the syllabus, then yeah. Just a second. Thank you.
I was like, where? I never saw a quiz.
Hey, cool. So tomorrow we're just going to come in here and we'll just talk about the solution to mission 2. And, or, here's a thought. Now, I don't know if this is going to be okay with you guys or not. We could skip tomorrow and just come back Monday and talk about things before test. So what's your preference? Here's your choices. Show votes. Skip Monday or skip Friday?
Ooh.
Yeah.
The quiz you were going to give us tomorrow, could we work it out as a class? Like you show us how to work these problems?
So we will meet tomorrow. Apparently we're not skipping class. Fine. Guilt me into it.
Wait, what?
Better about knowing how to do those problems in the test.
Yeah, she's got a point. I will stop my being lazy. All right, no skipping class. Fine. But, oh, how about this? I have a compromise. We skip tomorrow, but I post a quiz that could have happened if there was to be a quiz that we can discuss Monday. That also works?
Will you be posting solutions to it as well?
No. What's that? I mean, we have you have test 1 that was Math Battle 1, which is a complete, pretty representative test of what you're going over.
So you're saying you'll post it and we'll work it out or talk about it on Monday?
Did you post the solution after class on Monday?
Yes.
I will post a short quiz which addresses the thing that was not addressed already on the test. In particular, the problems based on today. I think that's the one thing that's missing, right? So no class tomorrow. If you want to come to talk to me tomorrow, you're welcome to. I'll be around.
Do you have office hours today?
Oh, my office hours are done. I'm office hours earlier today.